So yesterday we started to talk about chapter 4, right? So the main purpose of chapter 4 is to, extend the Fourier analysis from periodic signals to continuous time aperiodic signals. Right? So aperiodic signals are signals that are not periodic. Okay. So the main idea here is that we're going to obtain the Fourier analysis for aperiodic signals. Right? The key idea is to exploit the fact that aperiodic signals can be viewed as periodic signals with a period that goes to infinity. Okay, so if you have a periodic signal where the period goes to infinity, then it's essentially looking at only one replica of the signal. So we use this periodic square wave as an example, and in this example, you can see that when you have a periodic signal x of t, its Fourier series representation is basically a linear combination of complex exponentials at the frequencies that are integer multiples of omega naught. Okay? So basically, x of t is written as a linear combination of frequency components at integer multiples of omega naught, right? At k omega naught. Okay, so a periodic signal has discrete frequency components. Okay. Now, as you increase the period, capital T, then this omega naught becomes smaller, which means that the frequency components of this signal becomes denser and denser as the period increases. So we visualized this through this square wave example here. Right? So originally, if you have a square wave like this, you may be taking samples at these points here. But as you increase the period, right, these samples that you take become denser and denser. And the corresponding frequency components are sampled at frequency points that are closer and closer together. Okay. So then at the limit, when this t goes to infinity, you would expect that the frequency components of the signal would eventually reach a continuum of infinite number of frequencies. Okay? So we showed that through some derivations. Right? We showed through some derivations last time that indeed this is true. Right? A continuous time aperiodic signal in general can be written as a linear combination of a continuum of frequency components. Right? So when you're looking at a continuum of frequency components, we use an integral instead of a summation. Okay? So this is saying that an aperiodic signal can be written as a linear combination of infinitely number of frequency components, each one with the magnitude, each one scaled by this x of j omega, which we call the spectrum, right? Because this specifies how much of the signal x of t is contained, right, in the frequency omega. And to obtain x of j omega, right, you can obtain this by taking the integral of x of t times e to the minus j omega t. And you can view this as a form of inner product between x of t and the pure frequency component e to the j omega t. Right? So you can sort of view as inner product between x of t and e to the j omega t. Okay. So when you take the inner product of two vectors or two functions, you're essentially looking at the projection of x of t in the direction of e to the j omega t, right? How much of e to the j omega t is contained in the signal x of t. Okay. So these two relations here form what we call the Fourier transform pair. Okay. So when you use x of t to find the spectrum, capital X of j omega, right, this formula is called the Fourier transform of the signal x of t. And if you use the spectrum, right, to perform a linear combination of frequencies to obtain x of t, then this is called the inverse Fourier transform of the spectrum x of j omega. Okay? Right. So this is, right, basically the main theme of this chapter here. Okay? So given the time domain signal, you can find the frequency domain signal, and given the frequency domain signal, you can find the time domain signal. Right? This is a unique Fourier, they form a unique Fourier transform pair. Okay. All right, so we can look at a few examples. So in this example, we start out with x of t that is a single-sided decaying exponential. Okay. So to find the spectrum of this, right, we can apply the Fourier transform formula. So here, capital X of j omega is the integral of x of t times e to the minus j omega t dt. Okay? And if you substitute x of t inside, this becomes integral from 0 to infinity e to the minus at e to the minus j omega t dt. Okay. So this is limited to 0 to infinity because of this unit step function u of t. Okay. So the rest is just algebra. So you integrate this. This will give you 1 over minus a plus j omega. Okay. E to the minus a plus j omega t for t from 0 and infinity. Okay, and if you plug this in, you'll get 1 over a plus j omega. Okay? All right, so for convenience, we often like to write the imaginary part in the numerator. Right? So you can do that by multiplying both the numerator and denominator by a minus j omega, and that will give you a minus j omega over a squared plus omega squared. Okay? All right. So if you want to look further into the details of how this spectrum behaves, right, we can split them into the magnitude and phase. Okay? So the magnitude is just the square, the square root of the square of the real part plus the square root of the imaginary part. So we've done this calculation before, so let me just write down the result. All right, so this is 1 over, square root a squared plus omega squared. Okay? And the phase is minus arctangent of omega over a. Okay? All right, so if you plot them out, right? If you plot them out, you will see that x actually has a spectrum that peaks at omega equal to 0, right? So this signal has a large low-frequency component and has high-frequency components that decays as omega increases, okay? And the phase converges to pi over 2 towards minus infinity and minus pi over 2 towards infinite frequency. Okay. Okay, so this is just a practice to show how you can start from a time domain signal, use the Fourier transform formula to obtain the spectrum. Okay. All right, so we can look at another example. This is a single-sided decaying exponential. All right. So in the second example, we're looking at a double-sided decaying exponential. Right? So this thing decays the same way in both positive and negative time. Okay. So again, you can apply the Fourier transform formula. Okay. So this is the integral of e to the minus a t e to the minus j omega t dt. Okay. So we can split this into, because we have an absolute t here, right? We can split the integral into, positive t and negative t. So for negative t, we have e to the a t e to the minus j omega t dt. And for positive t, we have e to the minus at e to the minus j omega t dt. Okay. All right. Now, this part is exactly the same as before, right? This part is exactly this integral here, okay? And this part you can compute similarly. So let me just directly write down the result. So the second part we already obtained on the previous slide. And the first part you can obtain similarly as 1 over a minus j omega. Okay? Now notice that this is the complex conjugate of this. Okay, so when you add a complex number with its complex conjugate, then the outcome must be real. Okay, so indeed, if you combine these two terms, you will get 2a over a squared plus omega squared, which is indeed real. Okay. So if x is the spectrum is real, right, then it's not really necessary to write the magnitude and the phase, right? We can directly plot this real function out. And again, you see a peak at low frequency and rapidly decaying magnitude as frequency increases. Okay? All right. Now, one interesting thing to observe here is that, when you look at the spectrum, you can see that the width of the spectrum depends on the value a. Okay? So if a is larger, then the spectrum covers a wider range, whereas if a is smaller, you have a narrower spectrum, right? You have spectrum more concentrated around low frequency. Okay? Now, contrary to this, right, in the time domain, if you increase a, right, increase a gives you a larger spectrum. If you increase a, you actually have a time domain signal that decays faster in time, right? So you have a sharper signal in time. Whereas if you decrease a, right, if you're looking at a smaller value of a, then actually you have a time domain signal that decays slower. Okay? So you will see many of these, inverse relationship between time and frequency in many of these examples. Right? So usually when you have a wider spectrum, you will have a narrower pulse in time, and if you have a wider pulse in time, you will usually have a narrower spectrum. Okay? Right. Now, in this next example here, we have x of t that is a unit delta function, right? Unit impulse function. So a unit impulse is like a ultimately narrow signal in time. Okay? So if this is ultimately narrow in time, then what would you expect in the frequency domain? Right. Yeah, you would expect something that extends to infinite frequency, right? And that is indeed the case. Right. So if you work this out, you get x of j over omega, which is the integral of delta of t. Delta of t times e to the minus j omega t. Okay? And this is simply equal to 1. Okay? Right. Because, any function multiplied by delta of t, right? Because delta of t is non-zero only when t is equal to 0. So it's equivalent to look only at the value of this function at time 0, which gives you 1. So eventually you're just integrating over the delta function, which is equal to a constant 1. Okay. So this is saying a delta function in time right, if you have a delta function in time, then this corresponds to a spectrum that is a constant over all frequencies. Okay? All right. Now let's continue to look at some other examples. All right. So this is the example of a square wave signal. Okay? So in example 4.4, we have a square wave in the time domain. So x of t looks something like this. Okay, it is equal to 1 between minus t1 to t1 and 0 everywhere else. Okay. Now, what is the spectrum of this? What is the Fourier transform of this? Right, we can, again, apply this Fourier transform formula. This will give us the integral of e to the minus j omega t dt integrated from minus t1 to t1. Okay? So I'm integrating x of t times e to the minus j omega t, but x of t is just 1 between this range. Okay? All right, so this integral we already computed before in a previous example, and you can show that this will give you something that is in the form of a sinc function. Okay, so if you work out this integral, you will get something like this. Right? You'll get 2 times sine omega t1 over omega. Okay. So previously, when I introduced the sinc function, okay, previously when I introduced the sinc function, I defined it like this. Okay. Now, some textbooks do use this definition, okay, but in our textbook, they define the sinc function with additional scale pi in the front, okay? So to be consistent with the textbook, let's use this definition instead, okay? So following the textbook, we define sinc function like this, okay? So you're going to see these two different definitions in different contexts, okay? So whenever you see a sinc function, just try to verify which definition they're referring to. Okay. All right, so suppose I want to write this in the form of a sinc function, okay? So then I would need to have a pi both in the numerator, denominator, okay? And I want to have a common theta, right? Both inside sign and also in the denominator, okay? So this only requires some additional rescaling. So in fact, I can do that by multiplying pi and then dividing it back so that nothing changes, right? So inside here, omega t1, I multiply pi and divide it back so that nothing changes. And I want the same thing in the denominator. So I get pi omega t1 over pi. Okay. So then what's left? What's left here? Here I had a 2, right? Pi cancels out. I had an extra t1 here, so I should also multiply that to cancel it out. Okay? So with this, I can then write the spectrum as 2t1 sinc of omega t1 over pi. Okay. All right. Now, the advantage of defining it with an additional pi scale here is that now when you look at the sinc function, the 0 points will be occurring at integer values of theta. Okay, so previously when I defined it as sine of x over x, the 0 points are occurring at integer multiples of pi. Okay, but now if you use this additional scale pi in the definition, then the 0 points will occur at integer values of theta. Okay, so therefore, if you look at this, you will see that the shape of the spectrum should have a peak at omega equal to 0, right? That is equal to 2t1. And then you will see these 0 points when inside here is an integer, okay? So this occurs when omega is an integer multiple of pi over t1, okay? So you see a first 0 at pi over t1, then at 2 pi over t1, 3 pi over t1, and so on and so forth. Okay? Right. Now this is from the time domain going to the frequency domain, right? When you have a square wave in time, you will have a sinc function in the frequency domain. Okay. Now what if you have a square spectrum in the frequency domain, right? What if instead you have this square shape in the frequency domain, okay? Then you can show that through an inverse Fourier transform, you can show that the time domain would then take on the shape of a sinc function, okay? And you can do that by applying the inverse Fourier transform, right, which is 1 over 2 pi minus infinity to infinity xj omega e to the j omega t d omega. Okay? So x of j omega is 1 from minus w to w. So I can limit this to integral from minus w to w e to the j omega t d omega. Now, if you look at this integral here, this is exactly the same as this integral, except for a minus sign here, okay? But this minus sign doesn't really matter because this is symmetric. So the integral of this, right, will give you the same thing with t1 replaced with w and omega replaced with t. Okay, so you have 1 over 2 pi times 2 times sine of wt over t. Okay? Or you can write it in terms of a sinc function, which is w over pi, the sinc function of wt over pi. Okay. So again, this sinc function has a peak when t is equal to 0, and it has 0 points when this term inside is equal to an integer, right? So this whole thing is an integer if t is an integer multiple of pi over w, okay? So you can see here that x of t peaks at 0 and then has 0 points at integer multiples of pi over w. Okay. All right. So you can see through this example that when you have a square in time domain, you have a sinc in the frequency domain. And then conversely, if you have a square in the frequency domain, you have a sinc in the time domain. Okay? So there seems to be some duality between the time and frequency domain, right? There seems to be some symmetry or duality between the two. And this is not surprising because if you look at the formula of the Fourier transform, right, the Fourier transform and the inverse Fourier transform actually looks the same other than, this minus sign in the exponent, right, and this constant scale, okay? But otherwise, their form looks almost exactly the same, okay? So you would sort of expect the same relationship going from one to the other or from the other back to itself, okay? All right, so this property actually holds, more generally, right? This is what we call duality, right? You observe a duality between, okay, time and frequency domain. All right. Now, if you look a little bit closer at this result, right? So if you have this square shape in the frequency domain, you can see that this signal, the signal that you're referring to, has equal contributions from frequencies minus w up to w and 0 outside of this frequency band. Okay? Now, as w increases, right, as you have a wider and wider bandwidth, you can see that these 0 points in the time domain become closer and closer, okay? So when you have a wider spectrum, you actually have a, narrower pulse, right? You will have a narrower and narrower pulse, okay? So you again observe this relationship, okay, between a time and frequency domain, right? A wider bandwidth corresponds to a narrower pulse, and a narrower bandwidth corresponds to a wider pulse, okay? And this is illustrated in the following slide. Okay. Right, so here we're looking at 3 cases, right? So here, W1, right, is larger than W2 and larger than W3, okay? So when you have a large bandwidth, your pulse is very narrow, okay? But when you have a narrow bandwidth, the pulse becomes wider. Okay. So this actually holds in general, right? There is this general inverse relationship between time and frequency domain signals. Okay? And this result is actually pretty intuitive, right? Because when you have a narrow pulse, this means that your signal is varying rapidly over time. So when you vary rapidly over time, this typically means that your signal has higher frequency components, okay? Now, on the contrary, if you have signals that have a wider pulse, right, meaning that it varies slowly over time, then this probably means that its frequency components should be smaller, right? It should not contain too many high frequency components. Okay, so up to this point, we have introduced the Fourier transform to help us perform spectral analysis on aperiodic signals.